We are a curious lot. We search, invent, seek, explore till we uncover answers. Change drives us from the moth to the butterfly, from the clay to the pot. That is why at RK University we educate through discovery. We shape thinkers and self-learners, making knowledge an exciting journey. Opening new doors and steering into new horizons, our students are a generation of tomorrow, a timeless tribe of change makers. When the fire burns within them, we rouse it to scale greater heights. When ideas germinate, we support our students to become entrepreneurs and help them cultivate it to bring about revolutions of change. At RKU, they are the nucleus, surrounded by a circle of learning, nurtured by hands of knowledge. By giving them a global exposure, we allow understanding to seep through project-based learning. They get their hands dirty, assess real situations, unfold new theories in our labs, and find holistic answers to every hurdle that comes their way. Interweaving happiness and learning, the university provides a vibrant atmosphere to fashion well-rounded personalities who are people of thought, people of freedom. Powered by spirit of inquiry, they move into the world on wise words and firm foundations. Each day, they pave a path that arches forward for themselves and those that will follow. At RKU, we make worlds meet. We craft trailblazers who shape better futures. We look forward together, standing firm on today's lessons and the possibilities of tomorrow. For the world is not our oyster, the universe is.
Hello, good afternoon, everyone, all the participants of the online webinar of chromatography and electrochemistry. Welcome back again. Yeah, I've seen a really good response of yesterday, whatever our session was delivered by Dr. Jayesh Dalani. It was on the chromatography. Different aspects of the different chromatography has been explained by him. It was a really splendid presentation and splendid talk by Dr. Jayesh Thalani. And after the session, we have also received many of the appreciable email, calls, and messages. Thank you for all appreciation, all the participants. Today, we come up with the another very important aspects of chemistry, that is called electrochemistry. See, electrochemistry are usually taken into consideration when it is rightly in the application form. Otherwise, in the theoretical form, people are usually avoid it, but they don't know the potential of its application. I wish to give. I'm not going to take a session. Dr. Bhavin Dhaduk is going to take the session, as he is on the one of the remote places is going to operate. So in case of any difficulty, please have a patient. He'll be definitely taking care of your difficulties. But the electrochemistry, I wish to give a very small example how it is to be a very important, very in a very nutshell answer. That just couple of month back, one of my neighbor, his son has having one science project. He's going to participate in one of the science fair, and he came to me and he just asking me that, sir, you are taking a science, you are teaching a chemistry, your professor, please help me to do so and so, and this is my condition and this is so on. I said, okay, let's go. What you wanted to prepare? He said that I wanted to make anything which is a very cheapest one. So I took one day and thought of, and then the idea flash was of electrochemistry. What we prepared is we took a very easy available plastic bottle, water bottle, cut it from half, from the cap size, and we took it and the its opener size and side, and then make a two hole on the bottle cap, and then we inserted two pencil having it graphite both the end. We fill with water and we give DC current, means the cell which is available in the ready available in the market. We just gave a connection, fill with the water, and the magic happens. What magic happens? Very simple electrolysis of water. So one side hydrogen, another side is oxygen. Bubbling is formed, and that boy was really surprised that what is this? I said this is oxygen, and I was surprised when I visited his science fair. He didn't wrote a name because his creativity also very surprising that what he written on the science project. I suggested electrolysis of water as per my very hi-fi knowledge, which is not going to work anymore at a school level. But what he wrote is room freshener, and uh, uh, and I was surprised at how it is room freshener. And what he did, he just took a few drops of a perfume into the water and start electrolysis, and the entire room get fragrances. Do you understand? So, in a nutshell, I wish to say that he used his creativity. I gave electrochemistry. He made it a product, and then you'll be surprised that nowadays in the market, whatever the mosquito repellent machines, you people mostly uh, know it like All Out or Good Night or kind of machines are working on the very simple electrolysis. All the platings, gold platings, and all kind of the things are of electrolysis. So electrochemistry is a very vital role in the society. In every day in day out, you might be deal with the electrolysis. Or going to deliver session. At the end of the session, we have a question and answer. We will definitely take care about the uh, your questions and chats and inquiries. Our support team, Dr. Jayesh Salhani, and the myself are also going to watch the chat and trying to answer as yesterday we did, right? And plus, but your active participation is very much important in playing a vital role in this entire session. I hope I'm not going to waste much of your time. And let's, before you go to the session, I must say many of the participants have started type their name, which we have did yesterday. But those who have yet not type their name in the chat box, please do type your name in the chat box so that we can have attendance there. It will help us for different purposes, right? Thank you very much. Now we will go towards the upcoming session. Thank you very much.
So very good afternoon to all of you. Myself, Dr. Bhavin Dhaduk. I am working as assistant professor in School of Science, RK University, Rajkot. Yesterday, Dr. Jayesh Dhalani has delivered a lecture on chromatography and its advancement. It was a very informative for you. Today, we are going to discuss a technique which is a routine laboratory techniques used to find out the concentration of analytes. This technique is known as a potentiometry, and these techniques is lie under the electroanalytical techniques. So I think most of the students heard the name of this technique. So let's start with the first terminology. Uh, what is electroanalytical techniques? So electroanalytical techniques are a group of quantitative method that is used to measure the electrical property of analytes. So which kind of the electrical property of analyte we use to measure? The first one is a potential and second one is a charge. And these properties are changed with the concentration of analytes, means we can say that these properties are concentrated dependent. If the concentration of analyte is changed, the property will be changed. This techniques has a certain advantages. The first advantage is it is for a specific ion that have a particular oxidation state. As we know that all the elements have a different oxidation states. Let's take an example of Fe. it having a two different oxidation state. First one is a Fe+2 and second one is a Fe+3. Means we can say that these techniques provide the information about the specific ion and its oxidation state. Second advantage is it is a highly sensitive and applicable to the extremely diluted solutions. And third one, it provides the information about the activity of a chemical species. Here the activity, it is also known as effective concentrations. Generally activity terms is used for the real solutions. So here the question is that what is a real solutions? A real solution in which solute-solute and solute-solvent interactions are present. And due to this interaction, the thermodynamic property of the solution has changed. And the value of the delta E and delta V is less than or greater than 0. Let's we talk about the ideal solution. In ideal solutions, there is no interaction between the solute-solute and solute-solvent are present. Means we can say that the thermodynamic property does not change. Means delta value of the delta H is 0 and delta V is 0. So these properties has a certain disadvantages. The first disadvantage is the excess amount of the interferences ion is present in electrochemical cells. There is a deflection in current and the voltage is observed. And second disadvantage is these techniques are applicable to the highly acidic or highly basic solutions. So we can say that we are dealing with a highly acidic and highly basic solution. This technique does not give the exact results. Let's classify the electroanalytical techniques. It is classified into the two methods. First one is a interfacial method and second one is a bulk method. First is a bulk method. In a bulk method, overall property of the solution has been determined. And the best example of a bulk method is a measurement of a solution conductivity. So let's how we can measure the overall conductivity of a solutions. So let's take an example of a hydrochloric acids. Here we need to find out the molar conductance of a hydrochloric acid. So the molar conductance of a hydrochloric acid is a sum of molar conductance of H plus ion and the molar conductance of a Cl minus ion. And it is a principle of a Coleridge. So on the basis of Coleridge principle, we can find out the overall conductance of solutions. In interfacial method, property of ions has been determined at the electrode-electrolyte solution interface. And the example of interfacial method is a determination of a pH by using a glass electrode. At interface of electrode and electrolyte solution, generally redox reactions is taken place according to the flow of the current. If the flow of the current is from electrolyte to electrode, then the reduction reaction is taken place. When the current flow is from electrode to electrolyte, then the oxidation reaction is taken place. So interfacial method is sub-classified into the two methods. First method is a static method and second is a dynamic method. In the static method, no current is passed through the analyte solutions. And the example is a potentiometry. And second is a dynamic method in which the current is allowed to pass through the analyte solutions. The example is a coulometry. So in coulometry, we measure the how much amount of the analyte is deposited on the current when the magnitude of the current is fixed and which is allowed to pass through a solutions for a specific period of time. And this is the best example of a dynamic method. So on the basis of electrical properties, a variety of electroanalytical techniques have been developed, and out of which we are going to discuss only the one, and it is a potentiometry. So first we are going to review some notations briefly, and that is a knowledge of redox reactions, what is a Nernst equations, electrochemical cells, and the electrodes. So what is electrochemical cells? So there are the two type of electrochemical cells are available. First one is a galvanic cells, and second is a electrolytic cells, and both cells are work based on the transformation of energy. In galvanic cell, generally chemical energy converts into the electrical energy via spontaneous reactions, and the example is a dry cell, which is generally we are using to get the electricity. In electrolytic cell, electrical energy convert into the chemical energy. Means we provide the external electrical energy to derive the non-spontaneous reaction. And the example is a hydrolysis of water. During the hydrolysis of water, hydrogen gas and oxygen gas is produced at cathode and anode. Let's we break the galvanic cell. So in galvanic cell, redox reaction is taken place between the two different compartments that allow to transfer the electrons from one compartment to the another compartment. But here the movement of the electron is from anode to cathode. So due to this movement of the electron from anode to cathode, we get the electricity. But after the sum of the time, the movement of the electron from anode to cathode is completely stopped due to the production of a LJP. Means we can say that the cell reaction will be completely stopped due to the production of a LJP. So how we can eliminate this problem? So we can eliminate these problems by using a salt bridge. Generally, salt bridge used to maintain the neutrality of a cell, and the KCl, KNO3, NH4NO3 is generally used as a salt bridge. So here the question is that how the LJP is generated. Look at the figure, and suppose we taking an example of a Zn anode which is dipped into the ZnSO4 solution, and the copper cathode which is dipped into the copper sulfate solution. During the half anodic reactions, excess amount of the Zn plus 2 ion is produced in a left hand side compartment, and during the cathodic half cell reactions, excess amount of the sulfate minus ion is produced in a right hand side compartment. Means that left hand side compartment containing a excess amount of the positive charge, and a right hand side compartment containing a excess amount of a negatively charged. So we can say that the double layer is generated at the point of junction, and it is known as a LJP. And due to this LJP, we does not get the electricity, and we need to maintain the neutrality of electrochemical cells, and it is overcome by salt bridge. In electrolytic cell, the redox reaction taken place in a single compartment, so there is no requirement to maintaining the system's electrical neutrality. So we observed no LJP, and we does not require any salt bridge to maintain the neutrality. The similarity of the both the cell is a electrode. One is a anode and second one is a cathode. Anode generally during in on anode oxidation reaction is taken place, and on cathode reduction reaction is taken place. But here the dissimilarity of the both cell is a charge. In a electrolytic cell, generally the anode have a positive charge and cathode is a negative charge, while in a galvanic cells the anode has a negative charge and cathode has a positive charge. So how it happens? So as we know that in electrolytic cells we provide the external source of electrical energy to derive the non-spontaneous reactions. Means here the flow of the electron is from external source to the cathode, So the excess amount of the electrode is placed on a cathode surface, and that's why it's become a negative charge. So how we can find out the cell potentials? The cell potential is a difference between the two half cells, and the cell can be calculated by using a simple equation: is a E cell is equal to E cathode minus E anode. But this equation is generally used for the standard condition. So on the basis of the equations, we have one example, and here we calculate the cell potential of a given cells. We have a cell reactions, and the reduction potential of the cadmium is a minus 2.40 watt, and magnesium is a minus 237 watt, and the answer is a 1.97. So how we can calculate it? So by using a simple equations, E cell is equal to E cathode minus E anode. So here the which we having a two electrodes and both having a negative charge, and the which become a cathode and which become a anode. It is a question for us. So we have a condition that if the more positive reduction potential of a cathode is become a on a electrode is become a cathode. Here both having a negative charge, but cadmium have a more positive charge as compared to the magnesium, and that's why the cadmium become a cathode and magnesium become a anode. But generally we are using a Nernst equations for the regular cells. So we can calculate the cell potentials by using the Nernst equations also when it is not in a standard conditions. And the Nernst equation is a E cell is equal to E0 cells minus 0.059 divided by N log Q. Here the N is the number of electrons, F is a 96,500 coulombs, and the value of the T is a 298 Kelvin. The R is a gas constant, and it is a 8.314 joule per Kelvin. And here the Q is the reaction coefficient, and it is a concentration of a reduced form divided by the concentration of a oxidized form. So on the basis of these Nernst equations, we have a one question which was asked in the GSET examination 2013, and here we calculate the cell potential of a hydrogen electrode which is deep into the solution that having a pH 3. We have a 4 different options, and here the answer is D. So as we know that the half cell reaction for the hydrogen electrode is a 2H plus, that's getting the 2 electrodes and it's converted into the hydrogen gas. Now we use the Nernst equations for the calculating the cell potential of a hydrogen. So here the Nernst equation is a E cell is equal to E0 cell minus 0.059 divided by 2. Here we can take a 2 because the transfer of the electron is 2. Divide is a log into reduced form divided by the oxidized form. Here the reduced form is a hydrogen gas, and we put the value, or we consider the value of a hydrogen gas is 1. And the oxidized form is H plus ion, and it is in 2 molar, and that's why we write the H plus 2 square. So rewrite the equations, rearrange the equations, and finally we get the answer is E cell is equal to minus 0.177 watt. But this technique is a very lengthy, and it having a number of calculative steps, and it have it a time consuming process. But I give you the one simple equations to, so we can easily find out the cell potentials. So that is E is equal to minus 0.059 multiply pH. So here we having a same questions, but the pH is a 3. Same questions, and pH is a 3. So then put the value of the pH in above equations, and we get the answers. We having the same questions, but here the pH of the solution is a 0, And again, we have a same equations for it. E is equal to minus 0.059 multiply pH. We having a value of the pH is 0, and the whole terminology become a 0. Then E answer is a 0, 40. So let's move on the potentiometric titrations. The generally potentiometric titrations in which we measure the potential difference between the two electrodes as a function of volume of reagent added. In this case, so cell potential is totally depend on the concentration of ions. The cell potential is generally measured by using a two different electrode. First one is a reference electrode and second one is a indicator electrode. Reference electrode provides a stable and the potential is already known. So I give you the example of a reference electrode. It is a standard hydrogen electrode, and the cell potential of a standard hydrogen electrode is a 0 volt at 25 degree centigrade. And any changes in the cell potential related to the concentration of ion is measured by the indicator electrode, and Queen Hadron electrode is generally used during our routine practicals. So it is an example of an indicator electrodes. So let's take an example of a reference electrode. So standard hydrogen electrode is a best example of a reference electrode. The standard hydrogen electrode consists of a plate that is deep into the acid solution, and pure hydrogen gas is bubbled through it at a slow rate. And we earlier mentioned that the cell potential of a standard hydrogen electrode is 0 volt at a 25 degree centigrade. And the half cell of reaction is H plus, this getting the electron and convert into the hydrogen gas. But this electrode is generally we are not using in a regular purpose, because we have it is very difficult to maintain the pressure of the hydrogen gas. And second one is a hydrogen is generally absorbed on a platinum electrode at a reduced that's reduced the potential by converting into the hydride ions. Second example of a reference electrode is a saturated calomel electrode. The saturated calomel electrode consists of two tube. One is an inner tube and second is a outer tube. Inner tube is a fill-up, or it is a pack with a paste of elemental mercury, mercury chloride and the KCl, while the outer tube is filled with the saturated KCl solution. And the cell potential of a saturated calomel electrode is 0.244 volt at a 25 degree centigrade and 0.2376 volt at a 35 degree centigrade temperature. Means we can say that the cell potential of a standard calomel electrode, saturated calomel electrode, is a temperature dependent. When the temperature is increased, cell potential will be decreased. The half cell reactions is a mercury chloride getting the two electrons and convert into the elemental mercury with a release of a 2Cl minus ion. So we can say that the potential of the HCE is depend on the concentration of ion. As we know that at a higher temperature, solubility of the KCl minus ion is increases, so the potential is decreases. Let's move on the indicator electrode. So best example of an indicator electrode is a Queen Hadron electrode. So Queen Hadron is generally a equimolar or a equilibrium mixture of a quinone and hydroquinone. But this equilibrium will be disturbed at above 9 pH. So this electrode does not give the accurate results for the strongly basic solutions. The cell potential of a Queen Hadron electrode is a 0.699 volt at 25 degree centigrade temperature. Half cell of reaction is a Q, getting the electrons and getting the 2H plus ion convert into the hydroquinone. So generally the Queen Hadron electrode working as a cathode and also working as a anode. So if it is working as a cathode, so we having a Nernst equation for the determination of a pH, and it is a E cell is equal to E0 cell minus 0.059 pH. If the queen hydron electrode work as an anode, then we have a Nernst equations for the determination of pH is a E cell is equal to E0 cell plus 0.059 pH. So on the basis of this, cathodic and anodic reactions for determination of the pH of a queen hydron on the base by using a queen hydron, we have a one questions which is asked in the GSET examination 2015, and the question is that here we calculate the cell potential of a queen hydron at a pH 2, and we have a standard cell potential of a queen hydron is a 1.30 volt. We have a reactions in which the hydroquinone is converted into the quinone with a release of a 2H plus ion, the 2 electrons. Means we can say that this is the anodic half cell reactions. And we have a, if here we having a pH and we have a standard reduction potential, standard potential cell potential of a queen hydron. So we have a equations, Nernst equations for the anodic reaction is a E cell is equal to E0 cell plus 0.059 pH. So put the value of a standard cell potential of a queen hydron is a 1.3 and pH is 2. Then finally we can conclude the answer is a 1.42. So titrations. So generally photostometric having three different titrations. First one is acid-base titration, second one is a redox titration, and third one is a precipitation titrations. So here we covers only the two titrations. First is the acid-base and second is a redox. So in acid-base titration, take an example of a strong acid which is titrated by using a strong base solution. So in these titrations, a fixed volume of acid we are taking in a beaker. First we note down the cell potentials before the titrations. Means we can say that we measure the cell potential of a initial state without adding a base solution from the burette. Then we add the strong base solution drop by drops to the solution of a HCl, and here with each addition of a base the acid is neutralized. Means concentration of H plus ion is gradually decreased by each addition of a OH minus ion from the burette, and after the each additions we source the change in a potentials. At the equivalence point, all the H plus ion is completely neutralized by the OH minus ion, and that's why the maximum potential change is observed at the equivalence point. And after the addition of each base, the cell potential would be steady due to the presence of excess amount of OH minus ion. The equivalence points can be determined from the plot of potential versus volume of titrant and the plot of delta E divided by delta V against the volume of titrants. And on the basis of these graphs, we can find out the normality of a hydrochloric acid by using a simple equation is N1V1 is equal to N2V2. And during these titrations, we use the queen hydron powder as an indicator electrode, and saturated calomel electrode is used as a reference electrode. So how can we measure the pH at the equivalence point? So we have a simple equation, E cell is equal to E cathode minus E anode. Here the queen hydron used as a cathode and saturated calomel electrode is used at a anode. So we already knowing that if the queen hydron electrode is work as a cathode, so we have an equation for the determination of pH. So applied and put the value on the above equations. The E is equal to EQ cell minus 0.059 pH. And we are already knowing that the cell potential of a saturated calomel electrode is 0.242 watt. Now next, the EQ cell, we are already knowing that the standard cell potential of a queen hadron electrode is 0.699. So put the value on the above equations and rearrange the equations, and we get the final determination of pH of a given solution. And by using the equation is a pH is equal to E cell minus 0.457 divided by 0.59. So using the below equations, we also can determine the dissociation constant of a weak acid. As we know that at the half equivalence point, the concentration of a salt and the concentration of acid is already become equal. So for the weak acid at a half equivalence point, it's a pH is equal to pKa. And so we are already knowing that the Hetzelbeck equations for the determination of a dissociation constant of a weak acid, and it is a pH is equal to pKa plus log concentration of a cell divided by the concentration of acid. And as we know that at a half equivalence point, the concentration of the salt and concentration of acid become equal. So the value of this become 1. So the log of 1 is a 0. So finally we can conclude that the pH is equal to pK. The second titration is a redox titration, and we have an example of a titration of a ferrous sulfate ion, which is titrated against the cerium sulfate ions. We have a plot of potential versus a volume of cerium plus 4 ions, and the shape of the curve is like a S shape. At the initial state, the potential is due to the presence of excess amount of Fe plus 2 ion. And after the equivalence point, it is a potential, it is due to the excess amount of the cerium plus 4 ions. At the initial stage, the potential is calculated by using the Nernst equations, and it is a E cell is equal to 0.76 minus 0.059 divided by 1 log Fe plus 2 divided by Fe plus 3. And after the equivalence point, the potential is calculated by using the Nernst equation, and it is a E cell is equal to 1.16 minus 0.0592 divided by 2 log the reduced form divided by oxidized form. And as we know that at the equivalence point, the concentration of Fe plus 2 ion will be equal to the concentration of cerium plus 2 ion, cerium plus 4 ions. And similarly, the concentration of the Fe plus 3 ion will be equal to the concentration of cerium plus 3 ions. So all the ions are in a equilibrium. So we put the equilibrium constants for the represent the concentration of all the ions. So here the put the value of K in this in the below equation, and it is a 1. So log 1 is a 0. Then the right hand side terminology become a 0, and then we find out the E cell is equal to 1.16. And similarly for the initial state also. So at the equivalence point, the potential would be the average of a potential of a initial and the after the equivalence radius. The E average is equal to 0.76 plus 1.16 divided by 2. So answer is a 1.85 watt. So now I completed my presentations, and I hope it will become a very beneficiary for you. And if you have any queries or any doubt, please put the message on my email ID. In my email ID is Bhavin Dhaduk @rku.s. And now is the session is open for you. If you have any queries, then put the message on a chat box. So let's try to solve it one by one.
Hello everyone, that was a really amazing session on electrochemistry, very much focus on the potentiometry and difference between the two type of uh, electrochemistry that you have gone through, specifically electrochemical cell and electrolytic cell, and then different electrodes, their cell potential, how to calculate it, and some few glance of examples of GSAT questions that has been asked, and very easy way and quick answering way that has been given here. Now we'll try to see the questions. Let me see the questions. First question is first question. Yeah. Okay. I guess the first question was. mm, yeah. The first question was, can we use, let me see, can we use, somebody asked, potentiometry for bacterial activity, right? See, Dr. Dhaduk is operating from very remote places, so what he did is he has captured your questions and then try to provide answer to us, and we will forward to you, right? So the first question by the Nero, probably, yeah, respected sir, can we use the potentiometry for bacterial catalytic activity measurement? Yeah, yeah, you can. If you see, if you go, check literature, you will find the potentiometry is not only useful for the bacterial catalytic activity, but also for the enzymatic catalytic activity. Both, for both, it is very much useful. Yeah, you can. The first scholarly article that you find in Google will be the application of potentiometry in the bacterial and enzymatic catalysis. Yeah, second question. What is the condition in the electroplating? Which metal is at anode and which metal is at cathode? Yeah. So electroplating is following the Faraday rule. So obviously the amount of the metal deposited on the cathode. So the metal you wanted to plate on the cathode, on the another metal. So the base metal should be always cathode, right? Suppose if you wanted to plate your gold on silver, so your silver should be cathode, right? Right. So generally in electroplating we provide an external source of electricity that drives the reaction, and it is part of electrolytic cell. So that is the equation. So the metal that you wanted to plate, that electrolyte, will be plated over the metal. I guess you got the answer. जो भी आप मेटल पे आपको उसको प्लेटिंग करना है, तो जिस पे करना है, that base metal will be cathode always, because the amount will be deposited on the cathode. It is Faraday law. Can potentiometric titration find the end point of weak acid and weak base reaction? No, it is not possible. When a weak acid reacts with an equivalent amount of the weak base, completely neutralization does not occur, right? So for that, what you are going to do, as Dr. Dhaduk has explained, Kohlrausch law for the conductometric analysis that you have to go for, and you are going to see the Kohlrausch law. It is for weak acid and weak base. So with the help of Kohlrausch rule, Kohlrausch law, that lambda acetic acid that has been again dissociated, that rule you have to apply for the calculation. So you have to go for conductometry rather than potentiometry. Yeah. So I guess these are the major questions. There won't be many major questions are there, right? and I'll check again one any. Yeah, you will get a certificate. Some of have asked that the certification will be definitely given on the end of the webinar. Will verify all the attendance as you have been told to write your name. So those who have written the name will be definitely getting the certificate. Yeah, and any other. Yeah, the book has already been prescribed by Dr. Bhavin Dhaduk. Different methods are there. For physical chemistry, I probably see in a glass stone are extremely good. Semi glass stone also, and rather what Dr. Dhaduk has suggested would be better because I am not expert on that part of the chemistry, but although what I have read that we do. So thank you for joining with us, everyone. I again request to please go through the same link in future if you missed something, because it will be stay at YouTube all the time. And I also insisting that you also inform your friend that this link is again available. If they miss the session, those who are not able to join will be definitely more than welcome to join it again on the same link, and you'll be it will be broadcast forever for a long time. Okay. Also please join us. Our Facebook page, Instagram page is also available, and you can find a different webinar, upcoming webinars. There is a one MOOC course on COVID-19 that we have launched just before, so you will find all the information on our Facebook page, websites, and Instagram. And it is a very generalized form. It is not something that only chemistry or microbiology or zoology or any physics people or any layman can attend that course, and they'll be getting benefit about the COVID MOOC course. That is MOOC course which is pre-recorded. For that, the time is not constrained. You can watch at any point of time. You can pause it and you can again watch it at mid of the night, early in the morning, in afternoon, whenever you wanted to explore, you can, right? So thank you for staying with us since today. It was a really splendid experience with you. We also learned many things from your side by your questions, your enthusiasm. I hope you please go through our website and also our bird view pages, which is very exciting with the video that you have seen. Thank you very much. Goodbye.